So as with the other talk, a quick primer on what is IceCube. IceCube is a neutrino observatory that we deployed in the Antarctic ice shelf. So we drilled about a mile and a half long holes into the ice. So the ice shelf is about 2 miles deep, and drilled to nearly to the bottom and deployed 5,160 of what we call a digital optical module, or a DOM, which is basically a very sensitive light sensor. And then we have and then we're looking basically for light streaks in the that pass through our detector and do data readouts and point these back to sources in the night sky. Besides neutrino astronomy, IceCube has a very, very big science reach. So besides astrophysics, we also do neutrino physics, earth sciences, beyond standard model physics, and we also can test fundamental symmetry. So it's a novel instrument in multiple fields, and with this broad science reach comes a lot of ways that we have to process data in very specific ways. So different analyses or different science goals have different ways of interacting with the data and also then extracting information from the data. Similarly, as with any sort of particle physics-based experiment, we have to do a lot of simulation to make sure that we actually understand our detector and sort of have a best first guess or best first understanding of what is going on physically in the detector when we see our signals. So why are we looking at neutrinos? A large part, actually, like about 1/5 of our observatory is dark to traditional, quote unquote, traditional astronomy. Like in traditional astronomy, I mean anything that uses electromagnetic waves or light. So we just heard from LIGO is one of sort of the non-traditional or a new kid on the block in terms of quote unquote messengers. But let's say you have your optical observatories like LSST, which we'll hear about in the next talk, and then you have X-ray, gamma ray, and also microwave, which is I think another talk from SPT later this year. And 20% of that electromagnetic light gets absorbed at very high energies and at very large distances. That means there's about 20% of the universe we can't see in sort of quote unquote traditional astronomy. So we do need something like LIGO and then also IceCube to basically explore this sort of dark area of our understanding in the cosmos. So how does this work? So I mentioned that we have these very sensitive light detectors, and what we use is something called the Cherenkov effect, which is basically a sonic boom, but with light. So typically you see this in nuclear reactors or in test nuclear reactors when you see a bluish glow of the cooling water, and that is also Cherenkov light. So basically what happens is you have a neutrino coming in, it interacts inside the detector or even outside the detector, and you have secondary particles, typically muons, electrons, taus, whatever you want to call them, coming out, and then they're traveling through the ice, but they travel faster than the speed of light in the ice, meaning that they then are able to give off this blue radiation or bluish light that we can detect. And this is how basically IceCube operates. From a computing point of view, it is generally a very standard particle physics experiment. We have a global heterogeneous resource pool. Unlike the LHC, we have mostly shared and opportunistic resources, so we have limited dedicated resources. But the big part is that we use accelerators for ray tracing of this light through the detector that requires GPUs. We have a very broad physics reach and a high uptime, so we typically are up 99.9% of the time. So we have to do a lot of simulation to keep up with that data stream, and then also a wide variety of simulation to accommodate all the various physics goals. Similarly, we have to do some things in-house. So the standard packages of particle physics. So I'm picked out JN4 here, don't support everything that we do, or just don't exist. So for example, we have these niche dependencies like Corsica, which is an air shower simulation, but then also we operated at certain energies where JN4 doesn't support at this point. Similarly, we've had a significant change of our requirements over the course of the experiment. So we started as sort of a generic neutrino astronomy or neutrino astrophysics experiment, and then now we have these, we add accelerators to our resource mix. We have multi-orbit astrophysics as a new goal, and I'll go into that exactly what that means, and that brings requirements like alerting. The other big thing is, of course, here with the broad physics reach, we have a very high or a wide variety of resource requirements per job. So, for example, 10% of our jobs require more than 10 gigabytes of RAM, which is hard to find across the OSG. So on the new stuff here, so we are currently working on PyGuided 2.0, which we've talked about for several years. It basically is our sort of thin wrapper around HD Condor to submit jobs to non-OSG or EGI sites, so mostly HPC centers, NSF Exceed/Access centers, our targets here, or local campus clusters. The big change here is that we're switching to an OSG-based pilot, basically saying, we want to remove our private pilot and move to the OSG one, so everything looks a little bit more uniform, but also reduce the maintenance burden on our sites, that we basically only have to maintain a very simple set of scripts. So, and then the question comes up, why don't we do glided WMS and all the way? I mean, move hosted CEs, but I mean, setting up a hosted CE and et cetera, is still sort of the biggest hurdle that we have. Setting up CEs is just a lot more time intensive from our experience than it is to just use our thin wrapper scripts. And then also the CE is not necessarily, is a little bit too heavy weight than what we really need for most of these sites. Like there's a, unless we, really have a lot of resources at that site, we really don't need the heavy weightiness of the CE and gliding WMS. We also are working very closely with SDSC and UCSD on GPU provisioning for Kubernetes. So this is an outgrowth of our cloudburst from that we did in the last few years. So this the 2019 and 2020 cloudburst. We also did one in 2021. We basically had Google Cloud gave us some credits to test GPUs through their Kubernetes engine. And one thing that we also got access to was GPU sharing, which is in sort of a alpha beta stage, with them basically saying that Kubernetes can schedule multiple pods or containers on top that have access to the same GPU. But this is independent of the MIG technology that we see in the A100s or the A30s. This is similar to this vGPU that NVIDIA has for certain of the workstation GPUs, where multiple VMs can see the same GPU and they share the resources. In this case, the VRAM gets sliced up, and this is very similar. And so you can see here, if when we do some testing, at least with our software, across different first of all an A100 or a T4, and then sharing it, you can see that sharing a GPU basically doubles our throughputs, meaning that we get a lot more usage out of the GPU. Similarly, we can see the same thing with the A100s. If you basically enable MIG, you get for us, you get a much better throughput than with just the whole GPU, just because our software is more attuned to more GPUs rather than more slower GPUs than faster single GPUs. So similar to how the whole OSG works in terms of resources. Similarly, you can see that if we share the GPU, we get a similar speed up, but the issue is that the software is not 100%. So it's a little bit finicky in that respect. So, but the other big thing is that with this work with Google and their Kubernetes engine, we now have a new way to provision GPUs on PRP, which basically means we no longer need the gliding WMS and the CE to do that, but we can go talk directly to Kubernetes to provision the GPUs for our resource pool. So, in collaboration with Maron and Brian, we were awarded a CSSI for what we call the Event Workflow Management Service. This is basically trying to get the manager worker paradigm to a DHTC workload. So it's very related to the MapReduce for those who are familiar with Hadoop. The one big thing that we found is that plain HD Condor, at least, is not good for a manager worker paradigm. There's a scheduling overhead that dominates when you have a slow execution time. So this is similar to an OSG when we say, please have your jobs be at least 30 minutes to an hour. And we also want to use the right tool for the right job. HD Condor is really, really good at aggregating resources and scheduling across scheduling individual workers, but necessarily data management side is getting better, but it's not 100% there yet. In the message queues, so this is something like Apache Kafka or RabbitMQ, basically have all the tooling needed to extend HD Condor. So they handle many small data packages, so in this case, a message. They're multi-user, multi-workflow separation. We can have persistence of the data if needed. We can offload it. In some of them, we can offload it to other storage. There's built-in monitoring, and it's off the shelf. So basically, somebody else has done a lot of the legwork for us so we don't have to do some first principle derivation or some support in HD Condor itself. So why did we come up with this? So in IceCube, we already have a lot of experience with this event-based processing in two applications. So this is our messenger reconstruction, which I'll go into in detail, and something we call dynamic stack Corsica, which is our new way to feed the photon propagation algorithm efficiently with information. So we can see great speed ups with this. So 100 times for our multi-messenger reconstruction and 16 times for this air shower Monte Carlo. Both of these currently use 0MQ, but 0MQ really has its issues. It's only good on a special environment. So NPX is our internal cluster, and similarly on a single node is really where this 0MQ shines. Scaling is also an issue. So we can only get it up to 2,000 clients, and it's also fire and forget model. So meaning tracking of the individual data, and if the data gets lost, it is lost. So going a little bit more detail into the multi-messenger astrophysics part. So as LIGO's big event, LIGO's big observation, but we also had one which is this blazar called TSX 0506 plus 056. Basically, we initially found an event that pointed back to this, and then over the course of about a month, other observatories followed up on this and also saw a flare, basically a flare of that event. So we then also went into our back catalog of data and found that there were other flares of this event. This means that a fast response for this requires a significant amount of cyber infrastructure, meaning we need order several thousand cores for an hour or so. Just as a reference, a neutron star merger in this case would be sort of the ideal for the IceCube and LIGO observation. And if we wanted to do pure neutrino observation of core collapse supernova for IceCube and Dune would be an example. So how do we scale this construction? So basically, we were determining the direction of the event. Basically, we basically split the sky into constant surface area pieces, meaning that we split this. So as you can see here, we split a sphere into multiple sort of binning. We basically bin the sky into very small bins, or can bin into very small bins. Then we test hypotheses for each of these things. We basically create a map of the sky, and with basically saying, you know, this is the most this is the most probable location and direction with sort of an error around that. Each of these hypothesis calculations is independent, so we can easily split this workload up into basically as a number of bins that we use. So currently we do it in about 1,000 bins at a time, but theoretically we can do it up to 1 million bins. So this is how message passing would really help us, because the input and outputs are very, very small. So having something like this on top of Ichikondo would be fantastic. And that's it from my side.
Thank you, Benedikt. Any questions from the audience?